Hello everyone, Mystios here, and welcome to Malware Analysis for Beginners, where we look at common techniques used by malware and learn how to properly analyze them at a high level. In today's inaugural episode, we'll be looking at a very common anti-debugging technique known as isDebuggerPresent. So what is isDebuggerPresent? This technique is effectively a Windows API function that is found within the kernel 32.dll. So it is a built-in function within Windows systems. And as you might imagine from its name, basically what it does is it determines if the calling process is currently being debugged. Now, debuggers are a very, very common tool used from malware analysts, and the threat actors writing malware know this. So they like to use this function in order to determine if it is running on, a common end user machine, or if it might be getting analyzed by one of these malware analysts. Um, it's commonly used to evade this type of dynamic analysis. And the way it does that is it checks if it's in a debugger. And if it finds if it is within a debugger, it effectively changes the behavior of itself to perform some other action. So, for example, it may just immediately exit, or it may go into some sort of benign loop that just kind of is made to throw the analyst off. Regardless of what it does, it is behavior different than what it would be if it runs on a normal end user system. For this episode, we will be using a malware sample that can be found on my GitHub in the top of the description. Um, as with any malware sample, make sure that you are using proper uh, VM or lab isolation when analyzing it. I will say that this particular sample is one that I created myself, so I can confirm that it is not actually malicious. So if it were to accidentally run on a host system rather than a VM, it won't actually do anything. But it's best to treat every sample as if it were malicious in nature, just to kind of get in the habit of running it within that isolated environment. So if you'd like to follow along, you can find it in the GitHub as I mentioned. Otherwise, I will go through how to analyze that sample, how to find this particular function, and what we can do to effectively bypass it if we do find it in malware. Okay, so I have the sample in question here on my analysis system, appropriately named isDebuggerPresent.exe. So now generally what I like to do is just run the sample to see what it does. Now with a normal piece of malware, you generally would want tools open like Process Hacker or Procman to kind of record what's going on in the background. Since this is a self-built program that I know specifically what it does, I'm not going to do that in this scenario. I'm just going to execute it. So let's see what happens when it is just executed. Okay, so it looks like what it does is it pops up this message box that says, "Gotcha, this is malwares," and it has an OK button. Click OK, and it goes away and nothing else happens, presumably. Again, since this is a self-built program, I know that's all it does, but if it was a real malware sample, there may have been some things that happened in the background. So now what we want to do is, since we're looking specifically to see what this sample does when it's in a debugger, is to run it within a debugger. For this, we'll be using X32 debug, kind of the, I would say, de facto standard for debug analysis. So let's open it up within that. Okay, so again, what we want to do now is basically see what happens when it's running while debugged to see if there's any difference in behavior. So again, basically what we'll do is we'll run it from start to finish within the debugger to see what happens. So to do that, we basically go up to this run button, and you'll see here, this module right here kind of shows us where we are. We're currently not in the process itself, we're in the ntdll.dll file. So when we click run, we go to the entry point of our actual sample. So let's run it again. Okay, this time we get a message box again, but instead it says debugging, debugger detected with an OK. So we can see from this sample that it is able to determine that it is within a debugger, and it presents us with different information because of that. So now that we know that, Let's run our sample again. Let's run it to the point where it's our entry point. Now, there are multiple ways that a program can determine if it's in a debugger. And what I like to do in this situation is to right-click while within the module, search for current region, and intermodular calls. What this does is it shows us all of the different like Windows APIs or other sorts of calls externally that the program makes. And this can give us a lot of information as to what the program is capable of. So when we do that, we can search through the list, and the first one we see in the window is the isDebuggerPresent. If you ever see this within a malware sample, there's a very high chance that it is using this, again, to determine if it's in a debugger, and if so, perform a different function than if it was not. So from here, what we can do, it gives us the address where the call is made, is we can double click this. And then in the CPU window, it will take us to where this call is within the program. So what we want to do here then is, now that we know this is where in the program this particular Windows API is called, we can right click and toggle a breakpoint. This means that the next time we run this, it will stop at this address if it reaches it within its process flow. So let's click run. And as we can see, it has stopped at this call. So for now, just to kind of walk through the different memory addresses and instructions it does, let's just click this step over button. You could do this step into, but what that would do is it would take you within the isDebuggerPresent function, which is a bunch of Microsoft stuff that we don't really care. All we really care about is what is being returned from that function. So with that, let's step over. We go to the next line, and then the next one. And if you noticed here, down here it says jump is not taken, and you can see this blue line. Basically what this means is, in certain scenarios, if this was true, it would take this jump. But since it is not, it will just continue with the instructions. So if we click step over again, you'll see that we go to the next instructions. We don't follow the line. So again, let's just continue. We have another call, and then here's a call to message box W, which again is another Windows API that basically displays a message box. So when we click step over here, we get our debugger detected message box screen. So we know that with these three instructions, in its current state while being debugged, from this jump point, it doesn't take the jump, it just continues. And when it does continue, it shows us that debugger detected message. So the crux of what we're looking at here is basically in these three instructions: the call to isDebuggerPresent, this test function, and then this JE. So for those who aren't familiar with assembly instructions, let's look into more specifically what these three instructions do. Now that we know what the three important instructions in our program is, let's step through each one to see what each one does. So the first one is call. Call in assembly effectively just calls a function. It enters into a function. In this case, the function being called is isDebuggerPresent. As mentioned previously, isDebuggerPresent is a Windows built-in API function that effectively just checks to see whether the calling process is being debugged or not. What we care about in here is the return value. So the return value of isDebuggerPresent will be non-zero if the current process is running within a debugger. The return value will be 0 if the current process is not running in debugger. And it's important to note that in assembly, function returns are stored into the EAX register. So if we run our program through the debugger and it gets to this step, the Windows function isDebuggerPresent will determine that it is running within a debugger and return a non-zero. That non-zero value will then be stored into EAX for further processing. The next call was test EAX. Test is basically an equivalent to a bitwise AND operation. What the test instruction does is it performs the operation and then discards the result, but it does modify CPU flags within the program. Particularly the one that we care about in this scenario is the zero flag. All the zero flag is a yes or no as to whether or not the previous computational operation resulted in zero. So if the computation was zero, then the zero flag is set to one, meaning it's active. If a register is tested against itself, effectively what is going on is that the program is checking to see if that register's value currently is zero. And again, if the register does end up being zero, then that zero flag is set to one. So in this case, since we're testing EAX and the previous instruction was a call, we are effectively checking to see if the result of that call was zero or not. Finally, we have the JE isDebuggerPresent.351026. So JE is jump if equal. Basically what this does is it checks to see if that zero flag is set. If it is set, then it jumps to the location. Sometimes JE is known as jump if equal to zero, basically just because it specifically checks to see if that zero flag is set. So it will jump if zero flag is set. The isDebuggerPresent.351026 basically just means where in the program that will be jumped to if the conditions are met. So in this case, isDebuggerPresent is the name of our program that's running, and 351026 is the memory address that will be jumped to if that zero flag is set. One thing to note too is that JE is also synonymous with JZ, jump if zero. They effectively do the same thing. You just may see them used interchangeably depending on, a number of different factors. So with that, let's go through basically the process flow of these three instructions. So first, we have the call to isDebuggerPresent, which will return a non-zero value if the program is being debugged. Again, if it's not being debugged, it simply returns zero. Then it runs the test EAX. So this will check if the return is zero or not. So again, since the previous instruction was a call and the value of that return is stored into EAX, testing EAX is checking to see if the return of the call was zero. And again, if so, then that zero flag is set. Finally, the last instruction jumps if that zero flag is set. So if the result of the call was zero and the test validates that and sets the zero flag, the program will then jump to the specified memory address once it gets to that jump instruction because the zero flag is set. So now that we know a little bit more about what the instructions mean, what can we do to effectively bypass this? If this was a real malware sample, we wouldn't want it to know that it is in a debugger, especially since we know it performs different actions if so. We want the malware to think it's executing on a normal end user system so we can see all of the things it does in that sort of scenario. So we have a few different methods that we can do to basically bypass this debugger check. So for the first one, what we want to do is first, at the breakpoint where the isDebuggerPresent is called, is to step to the next instruction. So as mentioned previously, the isDebuggerPresent function returns a non-zero value if it is running in a debugger. It only returns zero if it is not found within the debugger. And this instruction right here, test EAX, is effectively checking to see if EAX is zero. Since we are in a debugger and isDebuggerPresent returns a non-zero value, this will be false because it won't be equal to zero. But what we can do here is right before the test is called, we can manually change the EAX register to zero, which would then make this statement true. And the way we can do this is over here in this right screen over here. This lists all of the registers and all of the flags currently in memory in the program. And as you can see here, EAX is currently set to 1 because again, isDebuggerPresent returns that because we are in a debugger. So to change this, all you have to do is double click it, change this to the value that you want, which in our case is 0. Click OK. Now the contents of the EAX register is 0. So let's go through this test EAX. Now you will see with this jump if equal to 0, we can see that the jump is taken. This is because when EAX was tested, it was 0 because we changed it to it. So now, instead of the program recognizing that it is in a debugger, it thinks it is not. So if we click step over again, it will jump down here and then go through its normal process flow and show us the this is malware's message box. So that's one way that you can bypass this particular type of function is when it goes through the test, just modify the register to whatever value it should be if the program is looking for whether it's in a debugger or not. Another method, and to get to that, we'll restart the program and then get to the debugger present call. Okay. So another method we could do instead of changing EAX is changing what's known as the 0 flag. So to do that, we can step over, and this time we will step over this test as well. So what happens when this test EAX is called, if it is determined that the value of that is indeed 0, this E flag over here called ZF, or 0 flag, is set to 1. If this is not 0 at the time of the test, then it will be 0. So basically, what we are doing, or what this jump is doing, is checking the 0 flag bit to see if it is set. If it is set, then it will make the jump. If it's not set, then it just continues the instructions as normal. So, just like changing the EAX register, we can simply double click on this and it'll shift the 0 flag to 1. So now this flag is set, meaning the 0 flag is set. And as you can see here in the debugger, the jump changed. So now the jump is being taken because the JE, or jump if equal to 0, which checks the 0 flag, is true. So it takes the jump. So again, step over, click, and there we go. We get the box we would expect when not run within a debugger. So those are two kind of, I'll call them temporary measures that you can do to bypass this particular anti-debugging technique. What if we wanted something a little more permanent? Um, so let's again get back to our call. So those techniques are great if you aren't constantly restarting the program, because obviously whenever you restart, all of that, the modifications you made are wiped clean. So if you restart this again and again, each time you're going to have to remember to basically change that EAX flag. So this next bypass is one that can be made a little more permanent within the actual program itself. So again, this time we're going to look at this jump if equal to 0 instruction. Since this is kind of the crux of what we're looking at when it comes to what process flow that this takes. So under normal process flow, basically we want this jump to be taken. If the jump is not taken, that means that the program recognizes it is in a debugger and performs the behavior that, we don't want or we don't really care about. It's not normal behavior. So what we can do is this JE is known as a conditional jump. It's conditional because it only jumps if it is the last test or computation is equal to 0. What we can do is we can actually turn this into a unconditional jump instead. Basically, what that means is that anytime this instruction is called, it will just jump. Regardless of any previous computations or anything like that, it jumps every single time. And the way we can do that is on this instruction, we can right click and go to assemble. You can also press the space hotkey. So this allows us to modify the instruction at that particular address. And one way to do this, like I mentioned, changing from a conditional jump to an unconditional, is simply change this JE into JMP. JMP is the instruction for an unconditional jump. Again, meaning anytime that instruction is hit, it just jumps, regardless of anything else. So we can click OK there, and then cancel. So now as you can see that instead of saying JE, this just says JMP. And we can see that the arrow here is red, meaning that it will be followed once that instruction is hit. So let's step over, and perfect. We go down to exactly where we need. Now, I had mentioned that this is more of a permanent way. In its current form, it is not permanent. If you were to restart this JMP would simply revert back to a JE. But what we can do is we can do what's called patching, which is effectively modifying the value on the binary on disk. And we can do that by going to right click and to patches right under the assemble. And what this will do is this will basically show us all of the modifications we have made within X32 debug to instructions. In this case, we've only made one, which is this JE to JMP. So that's perfect. Now what you do is you click patch file. And what this does is this writes a new file with everything exactly as it was in the original sample, except for the change that we made. So I'll just call it isDebuggerPresent underscore patched. Perfect. And you'll see 1 out of 1 patches applied. So it didn't modify this binary, but what it did was it created a new binary with that modification to it. So what we can do to verify that is we can go to File, Open, and then open that patched version instead of the original version. So let's jump into our program. Let's make sure that the breakpoint is still there, which it is. Perfect. And then run to the breakpoint. And as you can see now here on this instruction is no longer a JE, it is JMP. Meaning, if we step through this patched version, it will show us the non-debugged message box. So those are 3 ways that you can effectively bypass this sort of anti-debugging technique. So now that we've gone over 3 different techniques for how you can bypass this anti-debugging technique, you may be asking yourself, well, which one should I use? And my answer to that will be, it depends. The first 2 ones are great if you are finding yourself, not needing to constantly restart the debugging process and starting from scratch. Because each time you restart it, if you used the first or second technique, you will have to basically remember to change that when you get to that part of the program. That's not persistent. That's something that needs to be modified every single time. Whereas the third technique, you actually write that change to a file. So it will be persistent. However, that can cause issues in certain situations. Like, for example, say the malware later on down the road checks the SHA-256 hash of itself to see if it's been tampered with. In that case, that would cause issues because you have physically modified the file itself. So it really depends. I would say the first 2 techniques are more preferable, again, as long as you are not having to constantly restart the program just because they don't actually write anything to the program or change it in any significant way. If you are having to restart it though, then patching the file may be the better route to go just to get that persistence. But again, you have to be careful with that because it may cause issues later on down the road. Thank you all for watching this episode of Malware Analysis for Beginners. If you liked this video or found it useful, please feel free to hit that like button and subscribe for more content. It really helps me out and lets me know that you want more tutorial videos like this. Likewise, if you had any questions about anything covered in this video, or have any suggestions to make the content better, please leave a comment and I would be happy to assist. Thanks again for watching and see you in the next one.